Okay, picture this. A rugged, unpaved road, maybe winding through some remote hills.
Yeah.
It's bumpy, right? Sometimes muddy, always a bit of a challenge.
Definitely.
But for the communities it serves, this isn't just, dirt and gravel. It's basically a lifeline.
Absolutely. It's their connection to everything. Healthcare, schools, markets. Real economic opportunity often depends entirely on that road.
It's essential stuff.
That's exactly right. But these vital arteries, well, they're constantly battling the elements. Their very existence can be pretty precarious, easily disrupted by, well, nature.
So today we're doing a deep dive into these unsung heroes of rural development, the roads themselves. Our mission, to sort of uncover the engineering wisdom behind making these crucial pathways durable, accessible, and importantly, sustainable.
Yeah, and we've been digging into some pretty technical stuff. Field guides, manuals from the U.S. Department of Agriculture, the Mexican Institute of Transport, road maintenance experts.
Right. So for you, the listener, this is kind of a shortcut to understanding that complex dance between infrastructure and nature, how we try to ensure smoother, safer journeys for, well, countless communities.
Yeah.
Okay, let's kick things off by really unpacking the why. Why are these rural roads just so incredibly important, especially in those, really out-of-the-way places?
Fundamentally, they're the absolute backbone for social and economic development in small, often isolated communities. Think about mountainous areas or semi-desert regions. Access is tough to begin with.
Right. Geography is already a challenge.
Exactly. And these roads, they provide critical access to basic services, health clinics, maybe a hospital further out, schools. Without reliable roads, these communities are just severely limited. It's about connection, opportunity, human well-being, really.
That makes sense.
Yeah.
But if they're so vital, what's their biggest enemy? You mentioned battling the elements. What's the number one threat?
Oh, hands down, it's water. The principal enemy of dirt and gravel roads is water.
Water.
Okay. If it's not managed effectively, you get rapid, severe deterioration. We're talking erosion, potholes popping up everywhere, mud, thick mud.
Ugh.
All of that just drastically shortens the road's lifespan. It compromises the whole structure. It's relentless.
So it's not just inconvenient, like getting your socks wet in a puddle, as you might say.
Yeah.
It's like the water is actively taking the road apart.
Precisely. It undermines everything. And that's why, building or maintaining these roads isn't just about dumping some dirt.
Right. It can't be that simple.
No, it requires really careful planning and design right from the start. And there's a big emphasis now on being environmentally respectful, minimizing negative impacts, aiming for sustainable development. It's all wrapped up in what engineers call best management practices, or BMPs.
BMPs.
Yeah.
Okay, so what does that look like, practically speaking, on the ground? What are the key things you need for good road design right from the outset to build in that durability?
Well, it always starts with proper location and planning, choosing the best route to minimize disturbance and maximize stability. Then you need stable slopes that cuts into hillsides and the fills building up the roadbed. And it's not enough to just eyeball it. No, professionals use tools like clinometers, ABME levels, things to measure the grades precisely. That precision is absolutely critical to prevent erosion later on.
Okay, precision matters.
Hugely. And using good materials, obviously. Well-graded gravel or soil for the road base is essential for performance, for longevity, and of course, putting in erosion control measures from day one.
Right at the start.
Exactly. And even before construction, there's usually a thorough environmental analysis. This looks at long-term costs, social, environmental, financial, identifies potential irreversible impacts. The goal is always maximize usefulness, minimize problems.
Okay, so if water is the big bad guy here, how do these engineering guides tell us to, well, heroically manage it? What are the different ways you drain a road to fight back?
Heroically is a good word for it, because efficient drainage is without doubt the single most fundamental concept. It's king. And it generally breaks down into two main types. Surface drainage, dealing with the water you can see, and subsurface drainage, the water underneath.
Let's start with the surface stuff then. How do you handle the water flowing right there on the road?
Right. So surface drainage focuses on the water on the visible surface, the crown of the road. The road itself should have a slight slope, an incline.
Like a slight peak in the middle.
Exactly. Typically 2% to 4% for dirt or gravel. This keeps water from pooling, prevents hydroplaning. Very important.
Okay.
Then you have the side ditches, or cunetas. These are vital. They collect the water running off the crown and direct it away from the road.
The ditches along the side.
Precisely. They come in different shapes. Some are parabolic, sort of rounded, which can be good if vehicles need to cross them often. Others are simpler, triangular shapes. You see those a lot. They have specific dimensions, slopes.
Huh. More precision.
Always.
Yeah.
And safety is a factor, too. Sometimes you need barriers or warning signs if the ditch could be a hazard.
Makes sense.
And one more thing for surface water, sometimes you need intercepting trenches away from the road, like at the top of a cut slope or the bottom of an embankment. These catch runoff from the surrounding land before it even gets to the road.
Okay, so that's trapping the water before it causes trouble.
Exactly. Preventative measures.
All right, that covers the water on top. But you mentioned subsurface drainage. What about the water underneath? That invisible threat.
Yes. Subsurface drainage, absolutely crucial, maybe even more so in the long run.
Really? Why is that?
Because preventing the saturation of the road's underlying layers, the subgrade, the pavement layers, it significantly increases their strength, their bearing capacity. The whole road performs better.
Okay.
And it also helps stabilize slopes by controlling groundwater flow, reducing pressure within the soil. And economically, studies show that good subdrainage can extend a pavement's life by 2, even 3 times.
Wow, 2 to 3 times. That's huge. That really highlights how damaging that hidden water can be.
It really is a hidden enemy.
So where does all this underground water come from? And how do engineers actually capture it?
Well, the main source is usually precipitation, rain, snowmelt, either soaking directly into the ground near the road or seeping in from streams or reservoirs nearby.
Right.
It can also get in through cracks in paved surfaces or seep sideways from unlined shoulders or ditches. And sometimes you even get what's called artesian water, groundwater that's under pressure.
Okay, so it can come from multiple places. How do you drain it out?
Engineers use different types of drains. There are longitudinal drains, which run parallel to the road. Think of a trench alongside or under the road shoulder, filled with filter material, usually with a perforated pipe at the bottom.
To collect the water.
Exactly. They intercept water seeping in or help lower the water table. Then you have transversal drains. These cross under the road, often laid out in a sort of fishbone pattern.
Fishbone? Okay.
Yeah, they're really effective at draining water out of the road base and subbase layers, especially if the road cuts across the natural direction of groundwater flow. And finally, there are horizontal drains. These are a bit different. They're small diameter perforated pipes drilled, often with a slight upward angle, directly into slopes, cut slopes, or embankments.
Into the slope itself?
Yes. Their job is to drain water from within the slope, relieve internal water pressure, and directly improve stability. They can reach places conventional trench drains can't.
That sounds pretty specialized.
Yeah.
So many different systems working underground. What are the key principles behind designing these things effectively?
Well, effective drainage design hinges on understanding material properties.
Yeah.
Things like permeability, how easily water flows through a material, represented by a coefficient K in porosity, how much void space there is for water.
Okay, the K value.
Right. And the materials used, especially the gravel or crushed stone, they need to be hard, durable. Meet standards for fracture, abrasion resistance, soundness. Can't just use any old rock.
Quality matters.
Absolutely. And crucial components are the filter layers, or sometimes geotextile fabrics. These wrap around the drainage aggregate or pipe to stop fine soil particles from washing into the drain and clogging it up. A clogged drain is useless, right? So the filter is key to long-term function.
Right. Keeps the drain clean.
Exactly. And then all that collected water needs to go somewhere safely. It's usually discharged into the surface drainage system into a ditch, or often into a culvert or storm drain.
Which brings us to those bigger structures. What about when the road needs to cross a stream, or even a river? How are things like culverts and bridges designed to handle all that water?
Good question. Those are critical points. So alcantarillas, or culverts, are basically buried pipes or box structures that let water flow under the road.
The pipes under the road.
Yep. Used for small streams or to collect water from ditches, filters, downspouts, and pass it safely to the other side. How big they need to be? Well, that depends on hydrological calculations, figuring out the design flow, how much water to expect.
So you calculate the worst case scenario.
Pretty much, yeah. You design for a certain level of flood or flow. Sometimes, if the flow is very large, they might use multiple culverts side by side. These structures often have special inlets and outlets like head walls or wing walls to guide the water smoothly in and out.
Wing walls, those angled concrete bits.
Often, yes. Ideally angled at 45 degrees to guide the flow efficiently. And alignment matters too. Usually they follow the natural slope, but there needs to be a minimum slope, maybe 0.5% to 5%, so they clean themselves out and sediment doesn't build up inside.
Ah, self-cleaning. Smart.
Very important. Now, if you're in an area with lots of sediment, big rocks, debris, engineers might make the culvert bigger or build traps upstream or even decide a small bridge, a ponton, is a better option.
So sometimes a culvert isn't enough.
Exactly. There are even techniques like installing side-by-side culverts at slightly different heights to concentrate flow and sediment in the lower one, keeping the others clearer. And there's specialized software like HY8 that helps with the complex hydraulic design of these.
Okay, so that's culverts for smaller crossings.
Mhm.
What about the big ones? Rivers, deep ravines.
Then you need puentes bridges for larger crossings. Location is key here too. Ideally, you want a straight, stable section of the river, and the bridge should cross perpendicular to the flow if possible.
Why perpendicular?
Minimizes resistance, helps distribute the flow evenly under the bridge. You really want to avoid sharp river bends right at the bridge site.
Okay.
Bridges come in all sorts of designs and materials: timber logs, steel beams, fancy glued laminated wood, pre-stressed concrete. But the critical thing, regardless of material, is the structural design. It must be able to support the heaviest vehicles expected to use it safely.
Obviously crucial.
And the hydraulic side is just as critical. Designing a bridge involves detailed hydraulic analysis, understanding flow patterns, sediment movement, predicting floodwater levels. It's complex.
How do they figure all that out?
They use parameters like the river channel's roughness. How bumpy or smooth is the riverbed? Is it earth, rock, gravel? Are there obstacles, vegetation? All these affect how fast the water flows. There's a key number called Manningsen, the rugosity coefficient.
Manningsen.
Okay. Yeah, methods like Cowan's method calculate this by adding up values for all those different factors: channel material, irregularities, obstructions, vegetation, even seasonal changes. And again, sophisticated software like HECRS, the river analysis system, is used for comprehensive modeling, simulating the river flow, predicting how the bridge will impact it.
Wow, HECRAS. It sounds like serious modeling.
Eee.
Which leads me to think, if water is the enemy, then scour sounds like it's, I don't know, ultimate weapon.
Yeah.
How do engineers defend against that?
Scour. Yeah, that's a big one. It's a leading cause of bridge failures, actually. Scour is essentially the erosion of the stream by the water flow, especially during floods.
So the river is digging itself deeper around the bridge.
Exactly. There are two main types. General scour is like a widespread lowering of the riverbed, maybe along a straight stretch, or especially where the flow gets squeezed, like under the bridge itself. Then there's local scour.
Local.
Yeah, this is concentrated erosion right around the bridge foundations, the piers, those vertical supports in the water, and the abutments, where the bridge meets the land.
Targeting the supports.
Precisely. It's caused by intense turbulence, vortices like swirling whirlpools that form right at these obstructions and just dig away at the riverbed material.
That sounds incredibly destructive.
It can be. And it can happen in different conditions. Sometimes it's clear water scour, where the water is digging a hole but no new sediment is coming from upstream to fill it back in. Other times it's live bed scour, where sediment is moving so the hole might get partially refilled, but the digging action is still happening.
So how do you stop it? How do you protect against this scouring force?
Well, prevention starts, again, with good site selection stable, straight river sections, minimizing obstructions, and foundation design is critical. Making sure the bridge span is long enough and there's enough clearance or galibo between the highest expected water level and the bottom of the bridge deck. You don't want to constrict the flow.
Don't squeeze the river.
Pretty much. And then you need active protection. Armor.
Armor. Like what?
Protecting the riverbanks and the area right around the foundations. This involves using robust materials. You've probably seen riprap, large, loose rocks piled up.
Yeah, you see that a lot.
They dissipate the water's energy. There are also gabions, those wire cages filled with rocks.
Ah, the rock baskets.
Yep. Sometimes interlocking concrete shapes called tetrapods. Even things like repurposed used tires can sometimes be part of a system. And don't forget biology.
Biology?
Yeah, planting specific types of vegetation like vetiver grass can be a really effective, low-cost way to stabilize soil and control erosion.
Interesting. A green solution.
It's definitely part of the toolbox. Another technique is using spur dikes, or espigons. These are structures built out from the bank into the river channel.
To do what?
To deflect strong currents away from vulnerable spots like bridge foundations or eroding banks, sort of redirecting the attack. And just like with bridge hydraulics, that HECRAS software is heavily used here too, to model the river, predict how deep the scour might get, and design the right protection.
So we've gone from that simple image of a bumpy dirt road all the way to sophisticated computer modeling of river hydraulics and scour protection. It's quite a journey.
It really is. What seems like just a path is actually underpinned by incredibly complex engineering, hydrology, environmental science. It's all about designing resilience against nature, especially against water.
Every little feature, the crown, the ditch, the culvert, the bridge foundation, the riprap, it's all a carefully calculated response.
That's right. It's a constant dialogue, maybe even a battle with the environment. And the knowledge in these guides, it represents, decades, centuries even, of learning how to build these vital connections and make them last, even in really tough places.
So next time you're driving, maybe on a smooth highway, maybe on a less than perfect gravel road, just think about those unseen layers of engineering. The simple ditches, the complex subsurface drains, the hidden defenses against scours. All fundamental to keeping communities connected, especially those off the beaten path. Makes you wonder, doesn't it? What other invisible engineering marvels underpin our daily life, our safety, our convenience, and how much do we just take them completely for granted?